Good morning, everyone. We're going to continue this morning into Chapter 8. We're going to talk about the electronegativity of atoms and how that varies from left to right and the impact that has on bonds today. We'll then get into Lewis structures. We were getting in, and I was showing you the rules at the very end of class last time. We're going to look back at those rules and kind of build forward from there today. And so the electronegativity, this is probably one of the more important trends from, if we think of periodic trends on the periodic table. So if we're thinking of size, we know that size is decreasing towards fluorine on the periodic table. If we think of the second row, so lithium to fluorine, fluorine smaller than lithium. And then if we think the main reason there is the effective nuclear charge is changing a lot from left to right. So as we go from left to right, the effective charge is increasing. So we know fluorine is a relatively small atom with a relatively high positive charge. And so that's really good for fluorine in terms of it wanting to pull electrons towards itself. So imagine you're a nuclei and you have a high charge and you're particularly small. That's a good situation where that atom can pull electrons towards itself. Now, if you think of iodine, or if you think of towards the bottom right of the periodic table, those elements tend to have a higher effective nuclear charge. If you recall, effective nuclear charge increases from top to bottom, but those elements are bigger. So even though those elements have a higher charge, they're so big, they can't really pull electrons towards themselves. Now, this property of electronegativity, it's a property that the atom has when it forms a bond. So if we think of HF, or if we think of something like potassium fluoride or lithium fluoride, KF goes full plus minus. So when we start thinking what partial means, when I'm thinking partial positive with this delta symbol here, that just means partial where we have less than a full electron being exchanged. So instead of it being ionic, plus one electron, minus one electron, we might want to remember when we're writing our charges as plus and minus, we're exchanging one electron. So we're taking electron off of potassium onto fluorine, going K plus F minus. HF is somewhere in the middle. It's not fully perfectly nonpolar covalent. Nonpolar covalent would be something like F2, where if we look at the Lewis structure of F2, 7 valence electrons for each of the fluorines. They share their 1 valence electron in a single bond. Both the nuclei are exactly the same. So a tug of war happens with F2 where neither atom can pull that bonding pair electron closer towards itself. What electronegativity is it's a battle for the bonding pair electrons. And in the case of HF, because hydrogen now is a different nuclei than fluorine, hydrogen doesn't have the same pull because it has not as positive of a charge. It's not in the same size as fluorine in that regard. It doesn't have as strong of a pull for the electron. So the electron goes closer towards fluorine in HF. And there's a lot of interesting things that then happen as a result. One of the reasons, if you recall, that HF's not one of the 7 strong acids, it's actually because of these high charges are so attractive to each other that the fluorine keeps that hydrogen pretty strongly attached to it. And so that strengthens that bond and doesn't allow the hydrogen to be fully removed if you put HF into water. Now, like I said before, this doesn't make HF a safe compound to work with. HF is still probably the nastiest compound, or one of the nastiest compounds you can work with, because it reacts with your skin and can cause like nerve issues that can cause death. So again, just going back to just because HF is weak doesn't make it, and just because this bond is stronger doesn't make that something safe to work with. But it's this strengthening of this bond due to these charges that then have an attractive force together. It's in a similar way how we think of ionic bonding. You have the plus and minus charges, that strong electrostatic force of attraction between plus and minus ions. We can get that with these partial charges as well. And so if you notice, our left side elements have a relatively low electronegativity. Our right side elements have a generally higher electronegativity. And this goes back to the left side want to lose electrons. The right side are going to pull those electrons off those atoms. And it becomes either a scenario where it's metal, non-metal, and it's ionic. So KF, KCl, KBr, Ki, those are all ionic. We know those are all plus minuses where you fully have one electron transferred kind of permanently. In the case of non-metallic elements, you put hydrogen in place of any of the metals. You have H attached to carbon, nitrogen, oxygen, fluorine, etc. We're going to have a case where the bonds can be polarized in this regard, where one of the atoms is pulling more strongly towards itself, but not ionic. One of the things worth noting is how NO and F and chlorine, so let me choose a different color here. So these elements here, the ones in red, have the highest electronegativity. So the elements that are going to pull electrons most closely towards their nuclei are NO, F, and chlorine. And so you can know for sure if you have those atoms paired up with anything but themselves that bond has to be polar. So one of the things that we want to know here in chapter 8 is if we look at a bond, can we classify it as being maybe ionic or polar or non-polar, just kind of based on the atoms that are attached to it. Now, in some ways, you might want to think, well, what's the electronegativity difference that matters? And to me, that's not really the point. The point is almost if you take two atoms that are different, there's going to be some difference in charge, some difference in pull towards their nuclei. And certainly if you have one of the more electronegative atoms paired up with something, the bond has to be polar. We can look at a question like this one here, which bond is the most polar? So in terms of the greatest polarity, we're going to get the greatest difference of separation in the periodic table. So if you take the furthest right with the furthest left element, if you go down, if you notice electronegativity was decreasing downward, then we're going to get a bigger difference of electronegativity. So if we think of our periodic table and we're constructing it for these atoms here, we're going to have a big difference of electronegativity between N and F, smaller difference between O and F, no difference at all for F2. So the F2 bond, even though we have the two most electronegative atoms, this is the least polar of these bonds. So anytime you have two atoms bonded together, there has to be the two same atoms bonded together, then there's a difference of electronegativity that cancels out. There's no polarity there, there's no charge difference. And so NO, the difference between N and O is not going to be as great as the difference between N and F. We want the most electronegative with the least electronegative. And so between these choices here, it looks like the NF bond would have the greatest difference of electronegativity. N and Cl, if you actually look at their electronegativities, they're both 3.0, so their difference would be 0. But I would still call that bond polar. So if you take two atoms of electronegative that have different sizes, there's going to be a pull in those compounds, but the difference of electronegativity is so small, the NF bond is much greater difference, a more polar bond for NF. And same thing with NO, so smaller difference here for NO and NCl. And so one of the things we like to see is that the greater the difference of the separation of the elements in the periodic table. Generally, if you take fluorine or oxygen, two of the most electronegative elements, pair them up with something far away from those atoms, you're going to have the most polar bond. And then if you continue into the metal side, if you get all the way to like lithium, sodium, you're going to have a case where certainly that bond's ionic. So the more greater the separation, the more ionic character you could say too. So the greater the separation, the more polar the bond, we would generally say the more ionic character. And ionic character is kind of an idea of the higher the charges. That what the electronegativity difference is doing is it's creating those partial charges that are of higher magnitude. One of the things that's interesting is for diatomic molecules, and we could do this for larger molecules if we wanted to go into geometry and more complex arithmetic, we could show this for triatomic and larger molecules too, but for diatomic molecules here in this class, we can at least work out a way to kind of factor in what's the dipole moment of the molecule, and we'll talk about that in a minute, what that corresponds to, but it relates to the charges and the bond length. And so the dipole moment itself, it's symbolized by the symbol mu, is equal to the charges that are being separated. So if you think of those partial charges and call them Q, so if we have partial charge 1, so we have a partial, that would be the negative over here, and we have a partial positive over here. So in partial, again, think about the full positive would be plus 1 electron minus 1 electron. And so if we're thinking of the magnitude of this charge, it's probably less than the charge of 1 electron, is what we mean by being partial. And 1 electron's charge is 1.602 times 10 to the minus 19 coulombs. So that's just the charge of 1 electron. I would expect that you have that memorized. Should you need to know that on a test, we'd give that value there. So what we're saying is that the charge that's being separated by the atoms in a polar bond is going to be less than the charge of 1 electron. And then we just take the plus and the minus. So think about taking the magnitude of the charges that are being separated by some distance. That's R. So R is our bond distance. So R is the bond length of the molecule. That's an experimentally observable value. And so if you take the dipole moments for, say, HF, HCl, HBr, HI, or really any diatomic molecule, you can take their dipole moments and their bond lengths and try to work out what Q can be, or what Q would be, what that partial charge would be for that bond. And so we can come up with a relationship between the dipole moment, the bond length, and the charges. The only thing we might want to remind ourselves, there's a problem in the next slide that'll get into this. 1 angstrom is 10 to the minus 10 meters. And then we often use a non-SI unit for dipole moment. to make the dipole moments be whole number values. If you think about the charge being separated by some distance, this would probably be a really small number. So the conversion factor for the unit of D here, this one D stands for debye, named for Peter debye, but this is equal to 3.34 times 10 to the minus 30 coulomb meters. And again, not a number I'd expect you to memorize. If you need this on a test, we would give it to you. And so that's just a conversion factor for the charge that's being separated in coulombs by some distance in meters into this non-SI unit of debye. Now, the problem I'm going to show you on this slide here is really more just to kind of show you how you can take that data and then work it into charges. And really, I just want to see what is the magnitude of charge. I really don't expect to give you a problem like this on a test where you have to replicate the math, because really the math here is kind of boring. It's a little bit more just like memorizing and knowing how to use conversion factors. But I just want us to really see the problem kind of once, and then just to kind of see how we can work out what the charges are. And I just want to see how big the magnitude of charges are, because remember, it'd be plus 1 electron, minus 1 electron if HF were fully ionic. So this question here is asking us to go through HF with its given bond length and dipole moment. Can we calculate the charge on fluorine? We, at the same time, would calculate the charge on hydrogen. So we know HF should have a dipole moment pointing towards the fluorine. This arrow here is going to point, it's kind of where the electrons in the bond are slanting towards. It's pointing towards that partial negative charge. And so fluorine's going to be the negatively charged atom because it has a greater electronegativity than hydrogen. And so the way we can set up the math here is our dipole moment mu is equal to Q times R. We just have to account for units. Q is the charges, so the magnitude here is Q. So if we calculate Q, negative Q is the charge on fluorine, plus Q is the charge on hydrogen. So the magnitude of the charge being separated is Q. So Q is equal to mu over R. And so mu is the dipole moment. That's the 1.82 debye. We use that conversion factor to take it to coulomb meters. So 1 debye is 3.34 times 10 to the minus 30 coulomb meters. And we divide that by the bond length, 0.92 angstrom. Because you see the meter unit here, we want to convert that angstrom into meters. So 1 angstrom is a 10 to the minus 10 meter. Let's actually calculate this here, and then we'll convert it into electron charge units and talk about that very briefly. But if we want to do this calculation here, we're doing 1.82 times 3.34 E minus 30. We have like Planck's constant is to the minus 34. Sometimes you might think this is also minus 34. It is just to the minus 30 though. And then divide that by 0.92 times 10 to the minus 10. So I get 6.61 times 10 to the minus 20 coulombs. And that is less than 1.6 times 10 to the minus 19, right? That's the charge of 1 electron. So the charge of 1 electron, that was from Millikan's experiment, if you recall, was determining the mass and the charge of the electron. But so from the charge of the electron, we know that this is less than 1 full plus or minus unit for an electron. And so if we want to then say, well, what's the plus minus relative to the charge of an electron? We just take this number of coulombs, and just use that conversion factor for the electron charge. That's the charge of 1 electron. And so this kind of lets us see how partial of a charge it is. So we just divide that by 1.602, E minus 19. We get 0.41. We usually either use symbol E or E minus. It's the relative charge of the atoms in electron charge units. Now imagine this magically came out, if this were KF and it came out to 1.6, if the Q came out to be 1.6 times 10 to the minus 19, then we'd be converting and seeing that that's 1 electron, plus 1, minus 1. So for ionic, it would be plus and minus 1 electron. And for a partial bond here, you're seeing it's less than 1 electron, it's 0.41. And so for HF, being the greatest difference, you think HF to HCl to HBr to HI, for that trend, we're going to a lower and lower electronegativity difference as you go to chlorine to bromine to iodine. And so what that trend is doing is it's putting smaller positive charges on the atoms. So if you have a really polar bond, HF's among the most polar covalent bonds you can have. If you get more polar than that, you're generally on the ionic side, you're generally switching to a metal. So HF's difference is about as big of a difference as you can have for a bond that we consider to be covalent, and the charges are almost about half. So we're exchanging almost half an electron. Kind of gives you an idea. This probably isn't something to worry about for the test either, but we would probably say this is like 41% ionized, if you think of it that way. If you get all the way to plus 1, minus 1, that would be like 100% ionized. So we're kind of like in the middle of being 100% ionized and 0% covalent. We're like almost right smack in the middle with HF. And so when we look at the plus and minus charges on HF, we're about minus 0.41 on the fluorine, plus 0.41 on the hydrogen. And so the charges here are 0.41, or what we get for HF. If we go through the math just to see kind of what the result would be for HCl, the math would be 0.27 units of charge for HCl, so lower charges on HCl because the electronegativity difference is smaller. I believe it's 0.14. This is kind of off my memory. I think it's 0.14 for HBr and 0.07 for HI, or in that ballpark for HI. So as you're going to a smaller electronegativity difference between atoms, that's putting smaller charges on the atoms, which is serving to say that that bond would be less polar. And so this bond here, we'd say this is the most polar. And in some ways, maybe the dipole moment itself, that numerical value isn't always the best marker of polarity. The better marker of polarity is probably the actual charges. The magnitude of charge is going to be greatest for the more polar bond, and then the magnitude of difference is going to be smaller for a less polar bond. So if you make a bond that's not polar at all, like F2, Cl2, exactly 0 charges, so if the charges are 0, that's nonpolar covalent. If you have some charges on those atoms, then we would say that's a polar bond. Greatest possible charges, the most polar bond. The greatest electronegativity difference, that's going to be what leads to the charges being greater. So the electronegativity difference is putting bigger partial negative and positive charges on the bond, and that's giving us a more polar bond. To go to one last little detail here, the charge and the bond distance are kind of almost counter-opposing. If you just make the bond distance longer, but keep the electronegativity difference the same, and you just make a longer bond, you make the dipole moment bigger. So that's why I say it's really the charges are coming from the electronegativity difference, and then whatever the bond length is helps you determine the dipole moment. So the dipole moment itself, maybe not the best trend, because you'll see even for some larger molecules that have polar bonds, as we get into chapter 9, we'll start to try to look at multi-centered atoms. In terms of their properties, we'll try to look at things like CO2, which turns out to be nonpolar, versus water, which is polar, try to see why that is. So for larger molecules, we'll come back and revisit molecular polarity in chapter 9. So we'll kind of revisit the question in chapter 9 in terms of the entire molecule, is it polar? But here in this chapter, we're just looking at a bond. Is a bond polar or nonpolar? It's just a basis of its atoms and how different or separated they are in the periodic table. The greater the difference of separation, the greater the charges, the greater the polarity of that bond. Okay, so let's get into some Lewis structure rules for there's almost like 2 approaches for Lewis structures as we get into more complex Lewis structures, or maybe 3 approaches. One approach is if it's a simple molecule like O2, N2, water, CH4, molecules like that, we can probably just go to a Lewis dot structure. We might remember a lot of those Lewis structures from memory too, that's okay. So for really simple Lewis structures, we might be just applying like a really simple kind of like, either we know the structure already or we can come up with a dot structure. Whenever you look at a molecule and you say CO, and that sounds a little bit more complicated, I want us to then have for diatomics a thought that we're gonna try to have some driving force, which is satisfying the octet rule if we can. So for diatomic molecules, like the octet rule, 8 electrons per atoms, as long as you're not talking H, which just only gets 2, but we're going to try to satisfy the octets of the atoms by rule. As we get into the triatomics and larger molecules, the rules that we were looking at the very end of class on Friday, if we get into really big molecules, we're going to not necessarily worry first about the octet rule. We're going to kind of worry about that almost last. So for diatomics, we're going to try to satisfy the octet rule when possible. And so for carbon monoxide, it goes like this. And really, even for larger molecules, we kind of start this way too. We want to count up the valence electrons. We want to make sure that we look at the valence electrons. They're the ones that are going to be exchanged and try to make bonds with each other. 4 for carbon, 6 for oxygen, just periodic table placement. If you are getting valence counts wrong, or if you're not sure where we're getting valence counts from, this is a really important part of a Lewis structure. If we're making a mistake on that end, we got to make sure that we're just looking at where carbon is. It's 4 across, 2s2, 2p4, 4 valence electrons for the entire row of carbon, 3 for the row of boron, 2 for the row of beryllium, 1 for obviously the alkali group. We don't do too much Lewis structures with the transition metals, so we don't need to worry about too much or really at all about the transition metals. And then carbon's 4, nitrogen's rows 5, oxygen 6, fluorine 7. So it's really that simple, just looking at the row that the element is in the periodic table and making sure just to count the valence, the outermost electrons. So 10 for CO. And so what this means is how can I satisfy the octets on both atoms? If I think of a single bond, and we're also going to do this either single, double, or triple. And so if I think single, I can't satisfy the octet rule because it would have to be this. That's too many electrons. That's 14 electrons. And so that doesn't work because that's 14 electrons, so I have to do something else. So let me make a double bond and make this type of bond here like O2 does, but that's 12 electrons in the structure. I only have 10. And so I can't do that either, so let me try something else. So let me remove these electrons here and make a triple bond. And so then that's 10 electrons. And so that's what CO does. It forms with a triple bond, just like N2, and then it has one lone pair, and it has these 6 electrons being shared for a triple bond, so 6 bonding electrons. If I think of carbon, carbon has 8 electrons surrounding it. Oxygen has 8 electrons surrounding it, so 8 electrons for each atom. And then that is our best Lewis structure for CO because it's the only way we can satisfy the octet rule for both the C and the O atom. Now, if we then think, let me resketch over here so I don't have too much going on. And so I have this triple bond here. What's the partial charge on carbon? Remember how to calculate partial charges. Take the valence count that carbon has. So just go back to carbon's normal valence count, which is 4, and then subtract the number of electrons that are closest to carbon in this structure, and that's 5. So that gives carbon a -1 formal charge. So the formal charge of carbon in the structure is -1, and then the formal charge of oxygen, I have these 3 electrons, these 2. Oxygen should have 6 valence electrons surrounding it. Think of it this way. If oxygen has 6 electrons closest to it, its charge is neutral. If it picks up an electron, it goes negative. If it loses an electron from that count, it goes positive. And so what happened to oxygen in this Lewis structure is that it's lost an electron from its normal valence count of 6. We only have 5 electrons surrounding O, 1, 2, 3, 4, 5. That gives it a +1 formal charge. And now this seems strange. I hope this seems strange to you because we just talked about electronegativity. Oxygen is more electronegative than carbon. Why would a Lewis structure like this be the best Lewis structure for CO when we know oxygen really wants to pull electrons closer towards itself? Well, the answer is this just happens to be the case for CO. This is the only way that CO can actually exist. Now, oxygen is a little bit smarter than maybe what our Lewis structure is predicting, because remember, our formal charges is assuming that triple bond's equally shared. It's probably not equally shared. Oxygen's still smaller. Oxygen's still more electronegative. It's going to try to pull those electrons closer towards itself. An interesting problem, I think it's in one of the daily quizzes somewhere. If I give you the dipole moment and the bond length of CO, you can calculate the charge on C and O. The charge on O only ends up being 0.02 units of charge, not +1, -1. So the charges on CO truly are not +1, -1. But the charge on oxygen is truly positive. So the charge on oxygen in the real molecule is +0.02, and the charge on carbon ends up being -0.02. Like I said, there's a problem if I give you the bond length and the dipole moment where you can calculate those if you want. Probably not important to really do that on the test. I don't think we're going to throw you a math problem like that on the test, but you can see that carbon ends up still staying negative in CO. And that's ultimately, and we've talked about this already before, so I don't want to keep talking about like how carbon monoxide reacts in the body, but carbon monoxide will react through the carbon attached to your hemoglobin because of that negative charge on carbon. It would never have done that if there wasn't some negative charge building up on that carbon atom. O2, when it binds to your hemoglobin, binds to the only O, there's only O on O2, right? But so hemoglobin binds reversibly through the O and can be exchanged in your body. Carbon and carbon monoxide binds your hemoglobin through the carbon irreversibly to your hemoglobin. So your only chance of surviving a carbon monoxide poisoning is to get out of that situation as soon as possible so you can make more hemoglobin to replace that hemoglobin that's not like trash in your body and can't deliver O2 to where it's needed. So you suffocate yourself if you're in a CO environment. Okay, and that's really because of this negative charge. And the Lewis structure, if you think of the bond electronegativity, it doesn't help enough to kick oxygen into being more negatively charged. And so that's CO. If we look at NO+, how do we deal with charges? When I see this charge here, how does that factor into my valence count? Well, I still look at N, that's 5 electrons. 6 for O, that's just periodic table placement. And the positive charge is obtained by losing a valence shell electron. So whenever we see anions or cations, anions will add to the count, cations will take away from the count, and that's of the valence electrons. So I add up my valence electrons, periodic table placement, and then subtracting 1 for the positive charge. So that gives me 10 electrons overall. So NO with a positive charge has to have a triple bond just like CO did. There's no choice here. That's the only Lewis structure I can come up with that satisfies the octet rule for both atoms. And now if I think of calculating my formal charges, nitrogen is happy, if you will, because it should have 5 electrons closest to it, and it does. So it has a 0 formal charge. Oxygen is actually positive again. So oxygen is just like it was in CO, only has 5 electrons closest to it. So it's +1. So 0 +1 overall. The formal charges should sum up to the charge of the molecule. So the charge of the molecule is positive. So 0 +1 is positive. Now, again, this is kind of a case where you can imagine the triple bond is really going to shade itself closer towards the O. O is going to build back and gain back some of that charge that it was losing in the triple bond, such that it's not quite +1. So you can think formal charges are, assume the bonding pair electrons are perfectly shared equally between the two atoms, calculate their charges, and then kind of let go of that assumption and think what would happen. The electrons are going to shade towards the more electronegative O atom, because it's smaller and more positively charged, has a greater electronegativity. Now NO minus, 5 + 6 for N and O, but then +1 because this is minus. So we add an electron for the negative charge. That's of course 12 electrons. And so for our Lewis structure, for 12 electrons, we just go with this Lewis structure here. And that's the only choice we have. For 12 electrons, we'd have to do a double bond, and that gives each electron 8 electrons. So for the valence electrons, we're counting all these electrons here, so each atom has 8 electrons. Now in this Lewis structure, if we count oxygen, its electrons, we have 6 around O. So that's good for O to have a 0 formal charge. And nitrogen has 1, 2, 3, 4, 5, 6 around it. So nitrogen's formal charge is 5 - 6 for -1. Now, again, you might think, well, wait a minute, isn't O more electronegative? Doesn't oxygen want electrons more than O? Doesn't O want to pull electrons closer towards itself more than N? Why is N negative at the expense of O? Well, yeah, so this bond will polarize towards O. So O will actually build up a negative charge here as it pulls a bonding pair electrons closer towards itself, going on the partial negative side, driving down the partial negative charge on the nitrogen. So in the real molecule of NO, both atoms turn out to have a negative charge, but the formal charge is just based on the Lewis structure. Where do the charges kind of go, assuming the bonding pairs are equally charged or equally shared? Let go of the assumption, think about how the bond will pull more closely towards the O atom. Okay, so as we get into our triatomic and larger molecules, we have this set of rules here. We were just getting into these, so let's kind of go back through some of these. So we generally will always start by adding up the valence count. So even with the diatomics, we're doing this. So we're going to keep summing up our valence counts when we're doing our Lewis structures. We want to attach atoms to the central atom with single bonds first. So we're going to try to identify this central atom. This is usually pretty straightforward because it's usually something like if we have a molecule like SF4, like that S is the central atom. You know, usually the very first atom we give you, then the things after it are attached to it. If I give you then an H, then something after, the H is going to be attached to the central atom, then the other things too. So it's usually pretty easy to identify the central atom. But as we go along, if we have something that's a little bit more tricky to identify the central atom, I'll try to point it out. But it's usually the first atom. The book mentions that it's usually the lesser electronegative atom. That's not always going to be the case, but it's usually almost always the case when we write a Lewis structure. Like let's even do another molecule like OF2. Like O is the central atom. I mean, we're going to write that central atom first. It also is lesser electronegative, so it's usually not too hard to identify the central atom. But then for these Lewis structures here, it's like what we want to do for doing these Lewis structures, 6 for sulfur, 4 times 7 for the chlorines, that's 34 electrons. And then for OF2, we'd have 6 plus 2 times 7, so that's 20 valence electrons. And so if we start with single bonds, so for SF4, we start with 4 bonds here. One of the things I want us to always be thinking with Lewis structures is that we're not trying to imply the actual 3-dimensional shape of a molecule. So let's have in our mind here that a Lewis structure, I'm just trying to figure out how many bonds do I have? Are they single, double, or triple bonds? Where are lone pairs? How many lone pairs do each of the atoms have? In terms of the actual shape of the molecule, we're going to talk about that in chapter 9. So let's just try to have in the back of our mind, if we see a Lewis structure that looks like the molecule would be flat, that doesn't mean the molecule really is flat. And the Lewis structure isn't trying to think about how these bonds actually will kind of separate into 3-dimensional space. So we'll see that in chapter 9. But so here in this chapter, let's start with single bonds. Let's complete octets of our non-central atoms. So for SF4, 3 electron pairs are on each of the fluorines. There's 4 fluorines, so that's 8 for each fluorine. So that's 32 total. So what do I do with the 2 electrons that are not yet assigned? Well, if you think of the valence shell of fluorine, there's really nowhere to pack more. Fluorine wants electrons, don't get me wrong, but there's really nowhere else to put them. It's kind of like a neon atom, where neon, once it has that 2p6 configuration, has nowhere else to put electrons, so it doesn't really do anything. So our noble gases, to go back to a minute to the electronegativity chart, if you notice, there was no noble gas group on that chart because they don't form bonds. And so electronegativity is a property of things forming bonds. If the element doesn't form bonds, we don't have that property for it. And so the fluorines here are kind of adopting that configuration where they're completely filled with electrons. The only spot I can put electrons is on the central atom. So complete the octets of the non-central atoms with non-bonding electrons. And if there's unassigned electrons, like the 2 here, those go on to the central atom. And now the reason why we put them on the central atom is because now the bond polarities can help us. If you think about sulfur here, we would actually say that sulfur, count all the electrons around sulfur, that's 10 electrons. So sulfur has an expanded octet. It has an expanded octet in this Lewis structure. It's probably important to recognize that a Lewis structure is a model. The Lewis structure isn't real. It's just when I'm writing on this piece of paper. What I'm writing on this piece of paper doesn't compel the molecule to do what I'm writing. I'm just trying to understand what could the things, like how are the bonds likely to look that are connecting these atoms in a molecule like SF4. And just to give you also another thing that may seem, like from your vantage point, I don't know what you guys think, but the molecules I'm going to give you are real molecules. These are things that truly exist. You can put SF4 into like a container and ship it. So like we're generally not doing Lewis structures for hypothetical molecules that aren't likely to be stable. We're showing you structures that are things that can exist and do exist. But we're also not trying to lead you into the question, why does it exist? Why does this other thing not exist? It's more like, I want to give you a structure of something that's real so that you can think about how it might look like and how its bonds might arrange themselves on paper. So the goal here is go from formula to Lewis structures and just try to understand what we can understand from there and to think about some of the things that may go on in a real molecule. What goes on in the real molecule is this. Fluorines really are pulling those bonding pair electrons towards themselves. So if you think of what the fluorines do here, they're creating room for those 2 extra electrons on sulfur. So if you're saying we're putting all these electrons around sulfur, how do we do this? Well, what the fluorines do is they're pulling electrons away from the sulfur to make room for those 2 extra electrons based on their electronegativity. If I try to make a compound like SF4, where I choose a different element that's not as electronegative as fluorine, the compound doesn't exist and doesn't form. So we really need an electronegative atom to pull electrons away from the central atom in order to expand it, and in order to allow the central atom to expand its octet. Now, this expanded octet, this can only happen for 3rd row plus atoms. Just to give you an idea that if you see an expanded octet for a 2nd row atom, something's gone wrong. So we can only expand the octet of 3rd row and bigger atoms. This is kind of a consequence of us needing a larger atom. So an atom that's relatively small is going to be hard to pack more electrons around the central atom, even if we have really electronegative atoms pulling away. So if I try to make a molecule like OF4, like oxygen has the same count as sulfur in terms of valence count, oxygen's too small to have all these charged particles and charged groups that close to the atom. Makes sulfur now is bigger than O. Now we can have a compound like SF4 exist. OF2 though, this is actually a compound that exists between O and fluorine, where you just have 2 fluorines instead of 4. And so this structure here, we'd start with 2 fluorines attached. Again, I don't really care where I attach them. I'm gonna just draw them this way for the sake of space. I could draw this linear, like I'm not trying to imply really the shape of the molecule per se here, but that's 16 electrons because I have 8 around each of those fluorines. And so that's minus 16 electrons here. There's 4 electrons left over. So I go here and there onto the central atom. And so that's actually looks pretty good, right? Because the oxygen satisfies an octet. The fluorines are all satisfying an octet. If I calculate the formal charge of O here, the formal charge of O is 0, the fluorines are 0. If I go back to SF6, even with those 2 electrons around the central atom, I have, let me go a different color here. So I have 1, 2 for the lone pairs, and I have 1, 2, 3, 4 bonding pair electrons from the 4 bonds. That's 6 electrons closest to the sulfur. So 6 minus 6 for sulfur, so a 0 formal charge for sulfur, and then 0 for the fluorines. So SF4, kind of a peculiar Lewis structure, but it's happy with having those 2 extra electrons on sulfur. Gives sulfur a 0 formal charge, gives the fluorines a 0 formal charge. So let's look at this rule here. So if not enough electrons to give the non-central atom an octet, so if our central atom is deficient of an octet, doesn't quite have 8 electrons, then I might want to consider multiple bonds. So I might want to consider making a double bond or triple bond between atoms, the non-central atoms to the central atom. But what I want to do is I want to minimize magnitudes of formal charge in doing so. And I'll show some examples on the next slide as we continue what it would mean to minimize versus maximize formal charges. So in other words, I want to take charges, like I want a central atom that has a charge to pull the bond in so that we can lower the magnitudes of those formal charge. The octet rule would say we can't expand past 8 electrons. So when we're looking at this rule here, what does this mean? So the octet rule says, it's pretty hard to expand past 8 electrons. So should we expand octets with double bonds? We'll see a few examples where we can show you what a couple different Lewis structures might look like, so we might be able to weigh which one's better. The formal charge rule, this is kind of a weird rule here. We'll show this in a few Lewis structures, but the formal charge rule may allow octets to expand if it leads to lower magnitudes of charge. But again, the central atom has to be in the 3rd row of the periodic table. We cannot expand 2nd row octets. So just have in the back of your mind, if you're trying to expand an octet of a 2nd row atom, cannot do that by definition. And then we might be able to expand octets for 3rd row atoms and some Lewis structures, and we'll try to show examples of what these rules are getting at over the next couple slides. So we'll come back to some examples that highlight these rules as we continue. Okay, so CCl4, we may have done this last time, but let's just think of how we would do this Lewis structure. This time here, so I'd have 4 plus for carbon, 4 times 7 for the 4 chlorines, that's 32 electrons. Let me just write this over here to get this out of the way. So 4 for carbon, 4 times 7, 32 electrons overall. And so central carbon, 4 chlorines. Lone pairs around the chlorines. And so that's all 32 electrons, none left over for carbon. But that's good because carbon has a 0 formal charge, 4 minus 4. Chlorine's 7 minus 7. We could have gotten to this structure with a dot diagram too. We could have looked at chlorines and said they have 7, carbon has this like 4, like 4 valence electrons. We could have gotten here with like a Lewis dot structure too. So if you're looking at this saying, I would have just done like a Lewis dot diagram to get this Lewis structure, that's fine, that would work. Like for boron, you could look at boron and say, well, if it has 3 electrons, the fluorines have 7, so the fluorines look something kind of like this. We could make, a Lewis structure pretty easily for BF3 this way here. So that's fine for BF3 if you're thinking of it just in terms of a dot diagram. But if you come back to the rules, you get to the same Lewis structure. So if you apply the counting rules of 3 for boron, that's its valence count, 3 times 7 for the fluorines, that's 24 valence electrons. And so when we then distribute our bonds this way here, 8 around each of the fluorines, that's all 24 electrons, none left over. If you go back to the rules on the previous slide, on counting up the valence count, giving a single bonding the atoms to the central atom, so 3 fluorines attached to boron. And then if you think of giving octets to the non-central atoms, make sure you realize that we don't give an octet with lone pair electrons to the central atom. There's nothing in the rule that says to do this. And so we don't do that. That would be too many electrons. So we can't put 2 electrons there for boron, for BF3. So this is the Lewis structure for BF3 that we arrive at with our rules and with like a dot diagram. But the question would be, well, what do we do about the deficiency of an octet on boron? Should we do something here? And we did talk about this quickly, I think, on Friday, but the formal charge on boron right now is 0. 3 minus 3. Fluorines are all 7 minus 7. So formal charge-wise, we're pretty good right now. If we also think of what fluorines really are trying to do here, they're trying to pull electrons towards themselves. So fluorine's trying to steal those bonding pair electrons and put a partial positive charge on boron. So that's how the real molecule is going to try to exist, is the fluorines pull electrons off boron, put a positive charge on boron. Now, think about trying to do this here. What if we do this Lewis structure here where we make a double bond, just to try to think, should we satisfy the octet of boron? Because sometimes we think the octet rule is so important, we have to satisfy that octet rule. Well, what does that do to the formal charge of boron? So the formal charge of boron is now 3 minus 4, that's plus 1. Or excuse me, that's minus 1, not plus 1. That's minus 1. 3 minus 4 is minus 1. The fluorines would now be, instead of it being 7 minus 7, it's now 7 minus 6 for plus 1. So why on earth would fluorine adopt a positive charge so boron, an atom that doesn't even want electrons, goes negative in formal charge? Like, don't you see how that makes completely no sense at all? That boron actually wants to do the opposite. Boron is actually so happy to just give up the electrons that it had in the bonds and let fluorine steal those. So not only does this not happen, fluorine's actually stealing the electrons. So let's undo all this, kind of go back to where we started from. We just stay as is. And fluorines are trying to steal electrons off of boron, so boron can actually go partial positive. And the fluorines go partial negative. So the real molecule has negative charges around the fluorine atoms, a positive charge building up on boron, certainly not a negative charge on boron. All right, we did SF4 already on the previous slide, so we'll skip doing that here. And then for H2Cl, this kind of comes back to the like, how do we attach things that maybe aren't obvious in terms of a central atom? But like the hydrogens are attached to carbon, the oxygens are attached to carbon. I hope you see here that this is a pretty straightforward case of the 2 hydrogens on carbon, carbon's in the middle, so is the oxygen attached to carbon. So we're not trying to like really make you think of, should we put the O in the middle, should we put the C? We're literally telling you H2 to the C and then O to the C. So we're trying to tell you the atoms in some way that the way we're giving you the formula is implying the connectivity. So by the way we're telling you the formula should be implied that carbon's in the middle and that all 3 of those atoms are attached to it. And so then if we think of our valence count, 2 times 1 for hydrogen, because hydrogen just has 1 valence electron, 4 for carbon, 6 for O, so that's 12 total valence electrons. So if we think of our rules, or the Lewis structure rules, counting up our electrons, single bonding, give the non-central atoms an octet, but hydrogen's octet is good with just that single bond, so 2 electrons is good for hydrogen. So I don't want to do this, that's crazy. So we don't want to put any electrons around hydrogen. The bond pair is good for hydrogen's octet, so hydrogen's happy with 2 electrons, the other one with 2. This oxygen has 8, so it's octet satisfied. So now in this structure here, now we arrive kind of like BF3 at a case where we have 3 single bonds, but now carbon's formal charge is 4, should be 4. It only has 3 electrons closest to it. So I have this one, and and that one for these three here. That's +1. And then oxygen's formal charge should be 6, has 7, it's -1. So I have a -1 formal charge on O, +1 on carbon. And if there's anything I think we understand in the world of like physics is plus and minus attract. And so if we have a positively charged nuclei and we have room for electrons, why not pull in a multiple bond? So why not take these particles here, which are negatively charged, and pull them in to make a double bond? And so we make a double bond here for this molecule, H2CO. So we make a Lewis structure that looks like this, double bond. And now we've lost the lone pair off of oxygen to make that double bond. So we just took the lone pair electrons, moved them in to make the double bond. And then now we arrive at a structure where we've minimized the magnitudes of formal charge. Carbon's 4 - 4, oxygen 6 - 6. So we've reduced the magnitudes of formal charge by making the multiple bond. So that's when we want to make a multiple bond. So in BF3, we don't maximize formal charges. We don't increase the magnitudes of charge to make a double bond. We decrease the magnitudes of charge to make a double bond. And then we just don't want to, when we look at this carbon here, we just don't want to expand its octet. So the only thing we wouldn't want to do here is put more than 8 electrons around carbon because it's in the second row. So we just don't want to go past 8 electrons around carbon for a second row atom. And so this is a good Lewis structure for this molecule, which is formaldehyde. So pretty common compound here for H2CO. And so that's how, and really the idea here is we want a charge to pull in that multiple bond. We want a location for those electrons to exist. We want like an open octet to be filled by making that double bond in H2CO. Okay, so let's look at some Lewis structures, compare charges, formal charges, oxidation numbers, kind of come up with a linking between these three different numbers and reminding ourselves how they kind of relate back together. So if you recall from chapter 4, we did oxidation numbers. Remember by rule oxygen and hydrogen, so hydrogen would be plus, oxygen would be -2. Like remember how the fluorine goes -1 and OF2, so oxygen goes to +2 to kind of counterbalance those two minuses. So those are our oxidation numbers. And the oxidation numbers, if you recall back when we talked about these in chapter 4, I said for molecular compounds, these aren't really the true charges. These are really markers for the atoms that should be plus versus minus charged in the real molecule. So when I look at the Lewis structure of H2O, so I might start with this Lewis structure as just a dot diagram might be the easiest way to get to this. You could count the electrons, single bond, the non-centrals, count the electrons, attach the, you can go through the rules and get to the same Lewis structure for water. But we also probably remember this Lewis structure. We've probably seen it a million times. So this is the Lewis structure of O. The formal charges are all 0, 6 - 6 for O, 1 - 1 for H. And so the formal charges are all 0, but the formal charges are not the true charges. The true charges in the molecule, think of how oxygen's more electronegative. It goes partial negative, hydrogens go partial positive. So we get partial positive charges on the hydrogen, partial negative on the O. And what these signs here we're trying to do is predict which atom's positive and predict which atom's negative. And so the oxidation number signs should equal or be related to the true atoms that are positive versus negatively charged in the molecule. And so hydrogen being positive, oxygen being negative. And this is why then, if you go back to like NaCl dissolving in water, why we were showing that the O dissolves the Na+, because O carries a negative charge in water, and then the H's were surrounding the negative charge, because you get the plus negative attractive force. So compounds that dissolve in water are doing so because water has these built-in charges that can replace what were strong ionic forces of attraction with these strong attractive forces between water and that ion. So what about OF2? We did the Lewis structure earlier, so let's just write the Lewis structure. It looked much like water. So we had this Lewis structure here. If you recall, by the Lewis structure, we had, the formal charges would be 0 on fluorine, 0 on oxygen, 6 - 6, 7 - 7. But the true charges, which atom's more electronegative, O or F? Fluorine. So fluorine's going to pull the electrons closer towards itself and go partial negative, and oxygen, less electronegative, goes partial positive. And so we're predicting the negative charges and the positive charges based on the oxidation numbers. So the oxidation numbers aren't exactly equal to the charges because these compounds aren't ionic, of course, but we can predict the atoms that are plus versus minus charges if we think back to chapter 4 and oxidation numbers. Now we can expand octets in some Lewis structures like PF5 by almost having no choice, but it also is a stable compound that exists. PF5, we would just have 5 fluorines around phosphorus. I should have counted the electrons first, but I'll do that in a second. So let me count 5 for phosphorus. It's in the nitrogen group, so that's 5. And then 5 times 7 for fluorines, so that is 40. And so if I have 8 electrons on each fluorine, so lone pairs, sometimes I get this question, can you write the lone pairs as lines? That's fine. I mean, I'd rather write electron pairs as dots because I like to think of them as being 2 electrons. But whether you're writing lines or dots, it doesn't make any difference. Usually you'll see us write dots because I think it's a little bit more kind of accurate representation. But you can write either lines or pairs to signify lone pairs of electrons, either as 2 dots or a line in your Lewis structure. But that's all 40 electrons, none left over for the phosphorus to get any extra electrons. So phosphorus only has the 5 bonds surrounding it, but that shows an expanded octet. But that's okay, again, because phosphorus is in the second row, and this is something that truly exists. And so you can also think this probably is helpful to exist given that these bonds are really polar, and fluorines are really pulling those electrons back off of phosphorus to make room for all those electron pairs around the phosphorus atom. So phosphorus with 5 single bonds expands its octet to 10 total electrons in its Lewis structure. And if you think of the partial charges, partial negative for the fluorines, because greater electronegativity, partial positive for the phosphorus. And if you think of oxidation number rules, -1 plus 5. So oxidation numbers showing you fluorines are negatively charged, phosphorus positively charged. So ClF3 is another interesting compound in this category of kind of peculiar compounds that will show an expanded octet. Let's show why. We have 4 atoms all that are halogens, so we have 28 valence electrons. So I take a chlorine and I put my 3 fluorines attached. And so I have 8 electrons around each of the fluorines. That's only 24, the 28 electrons I have to assign. So there's 4 unassigned electrons. Where do I put them? I have no other choice but to put them onto the chlorine atom. And again, I'm not thinking too much about geometry just yet. In a way I am, because it's kind of what the molecule looks like. But we'll see why that is in the next chapter. But if you look at the structure here, I have 3 single bonds. If I think of chlorine's formal charge. What's chlorine's formal charge here? Should have 7, and I have, laser pointer, I have 1, 2, 3, 4, 5, 6, 7 electrons closest to chlorine. That's 0. And then fluorines, I have 1, 2, 3, 4, 5, 6, 7. So those are 7 minus 7s as well. So no formal charges building up, but the true charges do build up more on the fluorine because, again, fluorine's more electronegative, picks up the partial negative, and goes negative here. So the formal, the oxidation numbers would be -1 for the fluorine, and then +3 for the chlorine. So again, you're seeing, if you know the oxidation numbers, if you can think about those, are showing you where the actual charge should lie in a real molecule. The more negatively charged atom in the true molecule should be the negative atom by oxidation number rules. The more positively charged atom, the partial positive atom, should be the positively charged atom from the oxidation number rules. So we can do ions as well within these types of Lewis structures, and it just kind of makes us make sure how to count up the valence count. So we do 5 for nitrogen, +4 for the hydrogens, and then -1 for the charge. So that gives us 8 total electrons. And so the only thing we can do here is have 4 hydrogens attached to nitrogen. And then the hydrogens are all 1 minus 1, so those are all 0, but nitrogen is positively charged. And so then if we think of how this truly exists, the bond dipoles are going to point in towards the nitrogen because nitrogen's more electronegative than the hydrogens. So it's going to try to build back some of that positive charge that the Lewis structure is showing it has by the bond polarities. What about ICl4 minus? So 7 for iodine, 4 times 7 for the chlorines, +1 for the negative charge. So we add an electron for negative charge because we're adding to the electron count to go negative. If we're positive, we're taking away an electron. And so this is going to have a total of 36 electrons. And so iodine, chlorines all the way around. 4 of them, lone pairs. And then that's 32 electrons. 4 left over onto the iodine atom. And I know I'm rushing, but I just want to get the one thing here. So that I really want to start next time with NO3 minus, but I want you to see this twice if we can, because if we add it up, 5 for nitrogen, 3 times 6 for the O's, plus 1 for the negative charge, that's 24 total electrons. When we arrive at this structure here, 3 single bonded O's, but we have a 2 plus charge on nitrogen, minus on all the O's, but we're gonna stop here. Like we can only go to this structure here. And that's where we'll pick up next time, is trying to figure out why we don't make a second double bond. Because that would expand nitrogen's octet. So we stop here with NO3 minus, but then we gotta get into resonance. So we'll pick up with nitrate next time. Okay, so if you're a little confused how nitrate went fast, we'll pick up from that and build back from that at the start of class on Wednesday. Have a great day, everybody.